This video follows on from a previous video on equilibrium, which was equilibrium on a horizontal plane. Now we're looking at equilibrium on an inclined plane, and we're not including friction. That will follow after we've done a frictional video. So, for an object in contact with an inclined plane, there are always two forces which we can mark on without having to think. The first would always be the weight of the object, and secondly, because it's in contact with a surface, there would be a normal reaction, a normal contact force. We now wish to resolve our weight into two components. We've done that in a previous video, but in that video it was horizontal and vertical components. This time it's going to be components parallel to the incline and perpendicular to the incline. Now, if we have this angle alpha here, then this angle where the red blob is will be 90 minus alpha, and therefore it will make this angle here alpha. Once we've marked our angle alpha in, we can now get our components for our weight in that direction. So relative to alpha, this would be the opposite side. So this is going to be the sine component, and this, which would be the adjacent side, will be the cosine component. So it's mg sine alpha, which you can remember, if you like, as sine down the incline, and then into the plane, that's mg cos alpha. And then once we have those two components, we can remove the weight completely from the diagram. No need to have it there. Then we just remember the normal reaction, and those are the forces now parallel and perpendicular to the plane acting on the object. Now, for equilibrium, perpendicular to the plane, we will have R equals mg cos alpha, and parallel to the plane, we would need some force which would be stopping the object from moving down the incline. Because at the moment, we've only got one force parallel to the incline, which is the mg sine alpha, and therefore, as things stand, that object will start to accelerate down the incline. However, if we have a force up the incline, we can maintain equilibrium. So here's our example of trying to find the size of forces R and F if the object is in equilibrium. So we wish to resolve the weight component into its two components parallel and perpendicular to the incline. That's 30 degrees, so that will be 6g sine 30. Remember, sine down the incline if that helps. Into the plane, that will be 6g cos 30, and therefore for equilibrium, perpendicular to the incline, R will equal 6g cos 30, and then that gives us a value of R of 50.9 to three significant figures. Parallel to the incline, F equals 6g sine 30, and that's 29.4 newtons. In example 2, we have a horizontal force P acting, and therefore we would need to resolve that parallel and perpendicular to the incline, as well as the weight component. So parallel and perpendicular, the weight component will be, as we've seen a couple of times now, that will be sine down the incline, 10g sine 30, and into the incline, 10g cos 30. For the force P, I'm just moving that out of the way for convenience. For force P, that's 30 degrees there. It's the same angle as the incline. It would be a corresponding angle. So that would be 30 degrees. Therefore, relative to that 30, this would be the opposite side. So this is going to be the sine component. This would be the adjacent side. So this is going to be the cosine component. So up the incline we've got P cos 30, and into the incline we've got P sine 30. So putting our forces back, parallel to the incline we must have P cos 30 equals 10g sine 30, and that will give us a value of P 56.6 newtons. Perpendicular to the plane, R equals P sine 30 plus 10g cos 30, and that will give us 130 newtons to 3 significant figures. So the key part about all the examples that you've seen is to resolve any forces that are not already parallel and perpendicular to the incline, to resolve them parallel and perpendicular.